I've heard some about that down the line, yeah.
Okay, today's lesson we're going to look at diffraction and how diffraction occurs due to the interference of waves. Some of it we're referring back to Physics 20 and when we looked at wave interference, but mostly we're going to be dealing with new stuff, new formulas, and so on. A little bit of history and review of what we started with. So remember, Newton thought that light was a particle, and then there was a few experiments that proved that it was actually more of a wave. So Huygens was the first one. So remember, he was the one that kind of found the Poisson spot, and he figured out that the waves would diffract around an obstacle or an opening, and we get blurry edges in terms of a shadow. We get the dots in the circle when it goes around the side, and so on. So his sort of idea was pretty key to showing that light was a wave. And so he kind of drew this little diagram saying that if light's a wave, we can think of it as being just like a water wave. So when it hits an obstacle, it's going to go around it, and the waves would continue on the other side of the obstacle. So the hard part was they weren't really sure what the wavelength of light was. They assumed it to be small. So if you did it with too big of an opening, then you really didn't see much. So the hard part was to try to figure out how small the actual wavelengths are and to get gaps small enough to get it to actually cause some interference that they could measure. So Thomas Young was the first guy to sort of figure this issue out. So what he did was he did like a razor blade thin cuts. So a simple example would be if you took a piece of paper and you cut two little thin razor blade cuts into it as small as possible and as close together as possible. What we would think that is if light was a particle, then the light would go through those two cuts, and we would just get, just like spray paint, you just get two lines on the screen. But what ended up happening, and this proved that light was a wave, is the waves went through the thin cuts, and we got wave fronts, just like we see in this diagram here. So just like when we did water waves, we'd get the round waves would be overlapping, and any time you got two waves overlapping, we got constructive interference there. So in terms of, you have two waves, they go towards each other. Once they touch, we get one larger wave. So everywhere we see a red line is where we have constructive interference, and then the dark spot in between the lines would be where we have one wave up and one wave down. So when they construct, the wave would cancel out. So you get these series of bright lines and dark spots. So Thomas Young's experiment basically proved the fact that light had to be waves, and he tried it. He tried it a little bit differently, and he tried the cracks to be thinner and more cracks and less cracks and all that. But basically, the idea was he ended up always getting this kind of a band pattern where you get these pattern of lines, and the middle one always tended to be the brightest. So we think about round waves interfering, right? It's always the middle that gets the most overlap, so we get the most constructive interference in the middle. So that's why the middle one will be the brightest. So we call that one the central fringe, and we used to say being central, we sort of count it as position 0. Then on either side, let me just clear this off here again. So let's just kind of imagine we have two waves going. So we already know the middle one is going to be where they overlap the most. So right down the center we get the most overlap, so that would be the middle one. But then on either side of that, you're going to get the next or second most overlap. So we see that one as a fairly bright line, but not quite as bright. So we call that fringe 1, one space on either side. Then the next line would have the fewer number of overlaps, so it'll be not quite as bright. The third one not quite as bright, and so on. And eventually you just can't see them anymore because there's not enough interference to make it visible. What Thomas Young figured out is if he shined white light on a certain type of double slit, he ended up getting different colors. So we know that happens because each frequency of light, red being 700, violet being 350, they're going to refract differently, they're going to interfere differently, and once they combine, different frequencies will join up and make a new frequency so that you get a different color. It's not always going to be this color pattern. It's going to depend on what the details of the slits are, what the distance are between the slits and how far away and all those kind of things. So key thing to remember is we call our central fringe 0, and then we go 1, 2, 3, 4, and so on outwards from the center one. So what Young figured out was a formula to be able to calculate some of this stuff. So the formula is wavelength equals xd over nl. So x is our distance between the fringes. So you can see in this top diagram, x would be the distance between 0 and 1, or we'd say x is the distance between 0 and 2, or 0 and 3, and so on. So we just measure that x distance from the center one to whichever one we want, and the d distance is the distance between the slits that you cut. So that's usually given to you in the question. It'd say there are 100 lines per millimeter or something like that. So you'll get that distance. X is the distance between the images, the lines of the images. N stands for what number we're going to. So from the center to 1, we'd use an N of 1. From the center to 2, we'd use N of 2, and so on. And then L is the distance between the diffraction grating and the screen. So let's do an example. So wavelength equals xd over nl. So it says we've got a screen that's 13.7 meters apart. So that 13.7 would be our L. It's asking for the third order fringe, so that means we're looking for an N of 3. And it says we see these 2.5 centimeters from the center, so that'd be 2.5 centimeters to negative 2, so that's our x distance. And it says the D, the slits are cut 0.096 centimeters, that's 10 to the negative 2 as well. And it's asking what would the wavelength be and what would the color be. So when we do this calculation, we get 5.84 times 10 to the negative 7 meters, which would be 584 nanometers. And we know that red light is 700, green light's about 500, so this would be likely an orange type color. Okay, so the formula works pretty easy, and we can solve it for anything. You can solve for wavelength, you can solve it for X, you can solve it for D, any of those. There's also a slight variation of this formula, and we found out that this formula works good when the angle's small. If we're only going close to the central fringe, the numbers are pretty accurate. But if our angle starts to get a little bit bigger, what happens is the numbers change a little bit, and it's because it actually gets based on our distances. It would be better if the screen was curved. So that's why a movie theater and things like that, they usually have a curved screen to get a clearer or a sharper image. So once we get further out, that curve is going to make more of a difference. So then it's better to have a different formula. So if they give you a question, you don't have to figure out which one to use. You just based on whatever the question is. So if they give you a question where they give you that angle instead, so we still have n. So in this case, we'd have an n of 2. We're going from central to 2. Our d is still the distance between the diffraction grating, so that doesn't change. But now instead of using x and L as part of the triangle, we're just going to use the angle. So pretty simple to use this one as well. Just plug in the numbers. So for this case, it says yellow light has 540 nanometers. So that'd be 540 to the negative 9. And it says we have double slits, 2.2 to the negative 3 millimeters. So that'll actually be 2.2 to the negative 6 if we change it to meters. And it's looking for the angle, so that'd be sine theta. We want it from the central fringe to the second fringe, so divide by 2. So we do that calculation. We get sine theta equals 0.49. So if we do the second sine of that answer, we should get about 30 degrees. Let me just double check. I'm in radian mode. I'll switch to degree mode. So we get about 30.8 or 31 degrees approximately. Okay, so either of the two formulas, they work the same. Just one gives you distances, one gives you the angle, but just pick whichever one is appropriate. So a diffraction grating then is basically what we find out is the more slits we have, the more interference is going to occur, and the more interference we have, the better it's going to create the pattern. So if we only have 2 slits, you're likely only going to see 1 or 2 lines. If we have 3 slits, 4 slits, 4 million, the more you have, the better it's going to get. The problem though is if we were to make razor cuts into an object, eventually it's going to be too many cuts and it would sort of fall apart. So what they do now for diffraction grading is they actually take a piece of glass and they use diamond to etch lines in it. So the lines actually scratch the glass so the light doesn't pass through. So it sort of works the opposite. Where the line is, blocks the light, and then where the line isn't, the light will pass through the grating. And so they work just the same, and if we hold a diffraction grating up to white light, we'll see the different rainbow of colors because the different frequencies are diffracting differently. And if we use a monochromatic light, like a red laser or something like that, then we usually just see a band of red, and they would just be dots or dashes that will all be in red color. If we use diffraction gratings, we can actually measure the wavelength and get very, very accurate measurements. A true diffraction grating, they use glass and made with diamonds. What we would typically use is just a piece of plastic or acetate that has the scratches in it, but it works pretty good as well. And the key thing to remember is the violet end of the spectrum will diffract the least, and the red end would diffract the most. So if we were to shine a red laser and a violet laser at the same time, we'd see the red one like I have at the top here. So let's suppose the red scatters like that. But then if we did the exact same experiment with a violet, our center would be in the same spot, but we would see the second and third ones being a lot closer together because they diffract the least, so they're going to be a lot closer, where red would stretch out the most. And obviously green would be somewhere in the middle. And we can actually use a CD and a DVD to create rainbows and get these kind of things, because the grooves on a CD, so if you think of a CD just being a whole bunch of microscopic lines etched in with a laser, they basically work like a diffraction grating as well, and because the CD back is silver, it'll reflect what we see. So you can actually use a CD to bounce a laser off of and then reflect it onto a screen, and you would see a diffraction pattern occur exactly the same. And if you compare a CD to a DVD, the DVD will get a bigger refraction pattern or diffraction pattern because there's more grooves. A CD holds way less, so they have less lines cut in. A DVD way more. So the only thing you got to be careful of for a lot of these questions is quite often they'll give you the D number as how many lines per millimeter or how many lines per meter. So in this example, I've got that the diffraction grating has 600 lines per millimeter. So what we need to do is we need to figure out what that distance is between each line. So you just have to do the reciprocal. So 600 lines per millimeter, we just have to go 1 divided by 600, and that gives us 0.0016 repeating, and that'll give us millimeters between lines or per line. So then all we have to do is change that to meters. If we divide by 1,000 or times 10 to the negative 3, we would actually get 1.67 to the negative 6. So that'll be how many meters between each line. So quite often we have to do that calculation first, and then we can do the rest. So this last example, we've got saying what is the value of D. Or using the value of D, determine the color. So we've got wavelength. So we'd have D sine theta over N. So we just calculated the D, 1.67 to the negative 6. Our angle is 17.5 degrees, so sine 17.5, and we're doing the first fringe, so we just divide by 1. So if we go 1.67 to the negative 6, times it by sine 17.5, we get an answer of 5.02, so roughly 5, I'll put in 5.02, that's fine, times 10 to the negative 7 meters, which would be roughly 500 nanometers, and we know that 500 is green. So we'd have green light generated in this situation. So based on what we have got with our numbers, we get a 500 answer. We know that that's green. And that's it for diffraction.